Oh, that beastly number 5. So this is 1, 13, 15, and we're still talking about Zorba the darn mastiff. Number 5 on 4A. So, you know that we have Zorba, and Zorba is suspended by 2 cables which make a right angle with one another, and some other angle with the ceiling. We don't know what those angles are. We know that there is also a force of gravity down on Zorba. We know that force of tension 1 and force of tension 2 have a relationship where F of, let's see, the way I've drawn this, which one is F of T? Okay, let me change that to reflect what I did on my own paper. F of T2 is twice F of T1. Okay, so you've all got that so far? It doesn't matter. One of them is twice the other. You can call them A and B, you can call them blue and purple. So when I did it in these, just to make the picture match, we know that whichever cable makes a smaller angle with the ceiling is going to have the larger force of tension. So, and you remember that, you can think about that from the last problem where it said, what would happen if those cables got moved further apart? Oh, force of tension would increase. So we know that whichever one has got the smaller angle up here, so we would call this theta 2, this is theta 1, is going to have the larger force of tension. Okay, so the answer is, the angles are 63.3 and whatever its complement is, and one force of tension is 680 newtons, one is 13, I forget what the 1300 basically, 1360 newtons, but I forget what the raw answer is. So, okay. Let's start off with what? Sum of forces. That's where we start everything. So we know that we have, and I'm switching colors radically, I apologize. So if we start off with, we'll start off with our x-axis. Even though we have typically sort of disregarded the x-axis. Where the x-axis gets real useful is in creating expressions to solve for other things. So sum of forces on the x is equal to 0, because Zorba is not swinging from side to side, and that's equal to the force of tension 1 on the x plus the force of tension 2 on the x. And we know that those things are in opposition, so they're going to be negatives of one another. So what would force of tension on the x be? And we are using theta as an interior angle here, the angle which the cable makes with the ceiling. So your x-axis would be sine or cosine? 50-50 shot, folks. Cosine. Okay, so that is force of tension 1 times the cosine of theta 1 plus force of tension 2 times the cosine of theta 2. And that's equal to 0. Okay, so we have this relationship. Let's substitute in. So if f of t2 is equal to 2 times f of t1, we're going to rewrite this. F of t1 cosine theta 1 plus plus 2 times f of t1 times the cosine of theta 2. Yes? So far you're with me. Did we already do this part? Okay. So let's algebraically isolate. Well, we're going to do a couple things. We're going to get rid of our forces of tension here, because now we're just going to look at the relationship between the angles. So we know that the negative of f of t1 times the cosine of theta 1 equals 2 times f of t1 times the cosine of theta 2. Okay, so far so good. So we can divide both sides by f of t1 and we end up with the negative of cosine of theta 1 equals 2 times the cosine of theta 2. Great, we have a relationship. So, okay, now if we divide both sides by the cosine of theta 2, we have this relationship. From here, we can get our angles. Let me shrink this. So if we look at these two angles as part of a larger triangle, where we have theta 2 and theta 1, what relationship must exist with these angles? Pardon? They add up to 90. So that means that 90 degrees is equal to theta 1 plus theta 2. We now have a way to eliminate one of our variables. Yes? Make sense? Okay. And let's, I'm trying to remember which one I want to choose to get rid of here. I want 90 minus, okay, so therefore 90 minus theta 2 equals theta 1. Yes. Yeah. Oh, what? We're not done. We have a trig identity to do. So we have negative 1 times the cosine of 90, whoops, not 90, 90 minus theta 2.
Does it matter what?
Which one you do? No, it doesn't. I just wanted to use whatever was on top for me in this. I wanted the 90 minus a theta to be on the top here. Okay, and that is equal to 2. Now, here's the trig identity, folks. If you, and I'm going to have to shrink and move stuff. Okay, so if we take theta 2, for example, there's theta 2. There is opposite 2. There is adjacent 2. Okay? They all have the same hypotenuse. So the cosine, well, okay. The sine of theta 2 is equal to the opposite of 2 divided by the hypotenuse, right? So this side divided by hypotenuse. You all agree with this? Good. If we're looking at the cosine of 90 minus theta 2, which angle must we be looking at? This one, right? So if we're looking at the cosine of this angle, the cosine of theta 1 is equal to, oh hey look, O2 over hypotenuse. Because what's an opposite side for theta 2 is an adjacent side for theta 1. So it's a trig identity, it's just a true thing. That was just the way to prove it. Let me get this all shrunk. that for any angles within a triangle, the cosine of 90 minus theta 1 equals the sine of theta 2. Or I'm sorry, equals, pardon me, equals the sine of theta 1. So what we're going to end up with here, so the cosine of 90 minus any angle is equal to the sine of that angle. And that's a geometric proof. I guess we don't teach analytical geometry anymore as a separate standalone. When I was in school, we did. And you spent the whole year turning triangles on their heads and doing geometric proofs like that and trig identities. So what we've got here now, let's shrink something. Do that. Don't get confused by that. For any angle. So the cosine of 90 minus theta x, theta z, theta 14, theta 62, theta b is equal to the sine of theta b. You know, it's equal to the sine of that angle. So that's the important part. That's the trig identity part. Okay, so what that leaves us with is negative 1 times the sine of theta 2 over the cosine of theta 2 equals 2. Okay, one more trig identity. What's sine divided by cosine? Tangent! So negative 1 times the tangent of theta 2 is equal to 2. Now you can find theta 2. Go. Okay. And the negative, yeah, the negative 1 is a weirdo. The negative 1 ends up not mattering. It mattered a lot when those were forces. What we're saying, so what we get is negative 1 times 63.43, etc. degrees equals theta 2. All that's saying is that that angle is below the horizontal. It's below the level of the ceiling. Okay. Not really. You're just taking, you're just doing, okay, so it is negative 1 tangent, inverse tangent of 2 is equal to theta 2. So it's an inverse tangent function. Just the same way you found angles for headings all along. So now that you've got both angles, you should be able to find the forces of tension in the cables.
You use the negative in there?
You don't have to. There is some, I won't say it's, let's see, I've been watching too much British TV over break, controversy. No, I won't say there's a controversy, but I know that different instructors handle it different ways. There are folks who would have you, for every situation, take the angle on a 360-degree Cartesian coordinate system. I find that more confusing. You know, if you're doing it on a 360-degree round, then you would definitely have to use the negative. In this case, because you're looking for the value, you know where it lies in space, you can disregard the negative when using the angle. Does that answer the question? Was that helpful? Or
Yeah.
okay. Okay, good?